Ever thought about walking through a solid wall? Sounds impossible, right? Like something straight out of science fiction. But what if I told you that on the tiniest scales of reality, something kinda like that happens all the time? Today, we're going to dive into one of the weirdest, most brilliant ideas in all of physics, quantum tunneling.
And this slide right here, it just nails the whole paradox. In our everyday world, the rules are super simple. You throw a ball at a hill, but you don't throw it hard enough, well, it's coming right back down. Simple as that. But in the quantum world, the world of atoms, of electrons, the rule book gets completely tossed out. That same particle, it might just, poof, appear on the other side.
So what are we actually talking about here? Here's the official take. Quantum tunneling is this, spooky is a good word for it. This ability a particle has to pass through a barrier that, according to all the classical rules, it shouldn't be able to cross. Think of it like a ghost walking through a wall. But here's the kicker. It's not magic. It's real-deal physics.
Okay, so to really get how bizarre this is, we first have to ground ourselves in the world we know, the rules of our world.
Yeah, let's just stick with that simple analogy for a second. Picture this. You're standing at the bottom of a really steep hill, and you've got a ball. That hill, it's basically an energy barrier. To get the ball over to the other side, you've got to give it a big enough push, right? Enough kinetic energy to get it all the way to the top. And what happens if you don't give it enough of a push? Well, it goes up a little bit, gravity takes over, and it rolls right back to your feet. Every single time. No exceptions. See, in our world, energy is like a strict bouncer at a club. You either have the ticket to get in, enough energy to cross the barrier, or you don't. End of story.
But here's the question that changes everything. What if the rules were different? What if, for the absolute smallest things in the universe, the building blocks of you, me, and everything else, there was another way? A loophole?
And that loophole, that secret, has a name. The wave function. This is the moment we leave our comfy, predictable classical world behind and step into the weird and wonderful realm of probability. Okay, so here's the most important shift in thinking you need to make. A quantum particle, like an electron, isn't a tiny solid dot like a billiard ball. Nope. It's better to think of it as a cloud or a wave of probabilities. It's a mathematical way of describing all the places the particle could be. It doesn't have one single definite location until you actually look for it.
So check this out. When this probability wave hits a barrier, sure, most of it bounces back, just like our ball rolling back down the hill. But, and this is the mind-bending part, a tiny, tiny fraction of that wave actually leaks into and through the barrier. What that means is there's a small, but very, very real, non-zero chance that the particle will just suddenly be found on the other side. And in the quantum world, if something can happen, eventually it will. That's the tunnel.
Now, I know this might sound like some abstract, bizarre little quirk of physics that doesn't really matter. But it's not. Not at all. Quantum tunneling is actually one of the most fundamental processes in the entire universe. It powers everything from the stars burning in the sky to the very device you're watching this on right now. And yeah, this quote really puts it into perspective. Just let that sink in for a moment. Without this ghost in the machine stuff, none of us would be here. The sun itself wouldn't even be shining. So, deep inside the sun, you've got all these protons, and since they're all positively charged, they repel each other like crazy. The thing is, the temperature in the sun's core, it's actually not hot enough to smash them together with enough force to overcome that repulsion. According to classical physics, fusion just shouldn't be happening. But thanks to tunneling, two protons can get just close enough, and one of them will tunnel right through that energy barrier. That allows them to fuse and release all the energy that powers our entire solar system. It's incredible.
And it's not just happening way out in space, it's right here in your hands. Every time you save a file or a photo to your phone's flash memory, billions of electrons are tunneling through a tiny insulating wall to store that data. It's the key behind scanning tunneling microscopes, which let us literally see individual atoms. It's a process we've learned to control and engineer to run our entire modern world.
Okay, so particles can just pop through walls? This has to be breaking some major laws of physics, right? It feels like cheating. So how is this even allowed? Let's take a look at the actual rules that govern this insane leap.
This is probably the #1 question people ask. Doesn't this completely violate the conservation of energy? I mean, it really feels like the particle just got a free shot of energy to climb a hill it couldn't handle before. But believe it or not, that's not what's happening.
And here's the solution to that puzzle. No, the particle's total energy stays exactly the same the whole time.
It didn't break through the barrier and it didn't climb over it. Its very nature as a probability wave just means its existence isn't stuck on one side. The possibility of it being on the other side was always there, baked right into its wave function.
And this isn't just some random chaotic thing. It's probabilistic, sure, but it's also predictable. The odds of a particle tunneling depend on a few key things. You got a thinner barrier? Way easier to cross. A lower energy barrier? Also much easier. And the more energy the particle has to start with, the better its chances are. These are the exact rules that engineers use to build all those amazing devices we just talked about.
So, as we start to wrap this up, what's the big takeaway here? It's more than just a cool, weird fact. It's really a clue to a much, much deeper understanding of how reality itself works.
You know, the reason this all feels so strange, so counterintuitive, is simply because we're huge. We are made of trillions and trillions of atoms. The chances of every single one of those atoms tunneling through a solid wall at the exact same time is so ridiculously infinitesimally small, it would literally never happen in the entire age of the universe. But for one single electron, it happens constantly.
And that leads us to the most important point of all. Quantum tunneling doesn't break the laws of physics, it reveals them. It shows us that the universe, at its absolute most fundamental level, doesn't operate on the solid, definite certainties we're used to. It runs on a foundation of probability, of waves, of possibility.
And I just want to leave you with this idea. Particles aren't forcing their way through anything. There's no brute force involved. They are simply taking advantage of possibilities that only the quantum world allows. It's a reminder that there's this hidden probabilistic reality humming along just beneath the surface of everything we see, making all of it possible.